Predicting the future requires us to find order within chaos. To do that, we must mathematically separate underlying patterns from random temporary variations. Take these scatter plots. They map individual wages against age and education. Our objective isn't to guess a single person's exact salary, but to infer the relationship between these variables, identifying how a change in age specifically impacts a person's wage. In supervised learning, we categorize this data into inputs and outputs. The features we know, like age or education, are called X. The target we are trying to predict is the response, or Y. We can express the structure of reality with a single equation. Y equals f of x plus epsilon. The function, f of x, is the true relationship. It is the pure signal we are trying to learn. Then there is epsilon. This represents irreducible error, the inherent noise in the world that a mathematical function can never capture. To make accurate predictions, we must optimize our estimation of the function f of x, while accepting that the randomness of epsilon will always limit our precision. It seems logical that to capture the true function of x, we should use the most flexible, complex mathematical model available. We could use a parametric model, which makes simple assumptions like a straight line. Or we could use a highly flexible, non-parametric model that contorts its shape to fit every data point. However, these highly flexible models frequently produce wildly inaccurate predictions when they are used in the real world. To understand why this complexity leads to failure, we must observe how these models behave on unseen data. The failure of complex models is a measurable consequence of how statistical learning handles noise, and it is a hurdle we have to deconstruct to build better algorithms. To evaluate a model, we must divide our historical data into two isolated environments. First is the training data. This is typically 70% of the observations, and it is the only information the algorithm is allowed to see while it builds its mathematical rules. The remaining 30% is the test data. This is locked away and used exclusively to evaluate the model's final predictive performance. Once the model makes its predictions, we use mean squared error, or MSE, to measure the distance between those predictions and the actual observed data. Relying on training MSE is deceptive. Because the model has already seen those specific answers, it may have simply memorized them. A statistical model's worth is judged by how it handles the unseen feature, its mean squared error on the test data. This experiment shows error rates as flexibility increases. The black line represents the true relationship. The rigid orange line misses it entirely, while the hyperflexible green model zigzags to touch every point. On training data, the gray line shows error dropping towards 0. In this training environment, the hyperflexible model appears to be a total success. But look at the red test MSE line. It drops initially, reaches a minimum, and then rises sharply, forming a distinct U-shape. This spike is called overfitting. It happens because the model has started to map random noise instead of the actual signal. The optimal model is found at the lowest dip of that red curve, right before the overfit begins. Forcing a model to perfectly map training data doesn't reveal the truth. It memorizes the chaos and fails to predict reality. This U-curve doesn't always behave the same way. Its shape depends on the problem we are trying to solve. In this environment, the real-world relationship is almost perfectly linear. The red test MSE curve is nearly flat, meaning there is no benefit to using a more complex model. But in this nonlinear environment, the rigid model fails. The red curve drops steeply, showing that high flexibility is required before the overfit even starts. Simple assumptions work in simple environments, but complex data requires high flexibility. The ideal mathematical complexity is relative to the hidden geometry of the dataset itself. To understand why the U-curve forms, we must examine the two opposing mathematical forces at work. We can clearly decompose the expected test MSE into three parts: bias squared plus variance plus the variance of epsilon. Bias is the error that occurs when approximating complex reality with a model that is too simple. High bias means the model is blind to the nuances of the data, underfitting the truth. Variance refers to the model's instability. It measures how much the predicted curve would change if we used a different set of training data. Every algorithm enters this tug-of-war. If it is too rigid, it suffers from high bias. If it's too flexible, it's overwhelmed by variance. This light blue line shows bias plunging as flexibility increases. Simultaneously, the orange variance line skyrockets at high flexibility. Combined, they form the total test MSE. The dotted line marks where bias reduction perfectly neutralizes increasing variance. Moving left of this line increases bias. Moving right triggers high variance. Success in statistical learning requires finding this precise mathematical equilibrium between the two forces. There is one more term in our equation, the variance of epsilon. This noise exists regardless of the model's flexibility. Because of epsilon, the mean squared error can never reach zero. Since absolute predictive accuracy is a mathematical impossibility, we build balanced models designed to extract as much truth as possible from a noisy world.